So more on sequences. We're going to learn more about nonlinear sequences. Just to remind you, we started off with linear sequences. Our algebraic expression could look anything like this, where n is the number of the term, a is any number, a constant. It could be 1, and then it would just be n, right? It could be 2, 3, whatever, and any constant added. B could be negative, so it could be -3, or it could be +72, whatever. This is a linear sequence. You can tell because there is no exponent on the n. Then we looked at nonlinear sequences that could have these shapes. There would be an n with a squared or an n cubed. And of course it could be 2 times n squared or 3 times n squared, and there could be a number added as well. We also looked a little bit at 2 times n, where n is actually the exponent itself. It could be 2n or n plus 1, but n would be in the exponent, right? These were all examples of nonlinear sequences. Right, so we're going to look at this shape of nonlinear sequences where there's an n squared bit and an n bit. They're added together. All right. Let's say we have a sequence 6, 11, 18, 27, and so on. And they actually tell us that the formula for it is going to be any term in the sequence is going to be the number of the term squared plus b times the number of the term plus c. So in this expression, the b and the c are constants. They are constant numbers. The n in here is fine. We want that, right? In an algebraic expression that represents a sequence, that describes a sequence. This b and the c we need to find the value of, because we want to be able to plug in our n and find actual numbers. We can't have a b and a c in there. So what we need to do is find the value of b and the value of c. And this information gives us all we need to find these so that we can find the proper correct algebraic expression that we can use to plug in any n and find all the terms in the sequence. Okay, so what do? We actually know that term number 1 is 6, right? This is term 1, this is term 2, this is term 3, term 4. We have 4 values, so we can plug those in and use that to find b and c. So term 1 is 6, right? So let's write that like this. Term 1, the value of the term is 6. We already know that here. And 6 apparently was found by plugging in the 1 for n. So 1 squared plus b times 1 plus c. We can simplify this, right? 6 equals 1 plus b plus c. Okay. Oh, we can simplify it even further. We can subtract 1 from both sides and get 5 equals b plus c. All right. We have 2 unknowns, so this is not finished yet. Let's use the second term as well. Second term. The value of the second term is 11. So 11 equals this expression when we plug in 2, right? 2 squared plus b times 2 plus c. 11 equals 2 squared is 4 plus b times 2. I like changing that around so that it's 2b plus c. We could move the 4 over, or subtract 4 from both sides, I should say. 7 equals 2b plus c. We could change this into an expression that has c as its subject, so that we can then plug that in for the c down here. Let's do that. I'll just rewrite my 2 expressions that I found. Here I have 5 equals b plus c. I'm changing that so that c is the subject of the expression. I'm switching that around because I like c in front there. Right. This. And we have this one. 7 equals 2b plus c. Now I'm going to plug in c into this formula, right? So this I'm going to plug in for c. 7 equals 2b. I'm rewriting it, but instead of writing c, I'm going to write 5 minus b. Right? Because 5 minus b is the same thing as c. Now I have only b as my unknown, and I like that because now I can solve for b, right? 7 equals 2b plus 5 minus b, right? I can get rid of the parentheses just like that. I'm going to not take too many steps at a time. 2b minus b is b plus 5. I can subtract 5 from both sides. I always get stuck on the bottom of the paper. Subtract 5. 2 equals b, right? 2 equals b. It's important. So I have my b. This is a 2. So I can rewrite this right now and say, I know that it's going to be 2n because b is 2. Like I found down here, I'm just plugging that in for b. And then plus c. Now that I know b, oh look, I can solve for c right here. See how I can take this, oh, what color should I use? I can take this expression and plug in 2 for b, because we said b was 2. So c equals 5 minus 2. C equals 3. So I found my c. So I can rewrite my expression and say b was 2 and c we figured out was 3. And this is the final algebraic expression. I only have n here as a variable, as the unknown, right? So I can now use this to find any term in the sequence. If we look at our stuff that we did before, here, these were the simple cubed and squared sequences, right? And we looked at the difference between the terms and then the difference between the differences. We are going to now call this the first difference, right? The first difference between the actual terms are 3, 5, 7, 9, and 8, right? The differences between those differences, we're not going to call differences between the differences anymore, but we're just going to call them the second differences, right? In a squared sequence, the second differences were all the same, right? If we look at our cubed sequence, this is the actual sequence. This is the first difference. They're still all different. These are the second differences. And they're all different. The third difference, they were all the same. These are all 6, right? So this you need to know in order to do the next type of problem. So what we did here, where is it? Here, in this somewhat simpler example, there was no constant in front of the n squared. See that? We only had a b and a c. There's nothing in front of the n squared. In this new type of problem, we're going to have an a in front there. So let's say there's an expression describing a sequence, and it has, just like I said, bn plus c. So it's the same as the other one, except there's now an a in front of the n squared. So there's actually 3 unknowns here. Let's say we have this sequence, 6, 13, 24, 39, 58, and this expression describes this sequence. Now how are we going to find the values for a, b, and c? Okay, what we're going to do is find the first differences first. These are 7, 9, no, it's 11, 15, 19. Okay, they're not the same. I'm going to find our second differences. 4, 4, 4. Okay, the second differences are all the same, so we know that it's a quadratic sequence, like I showed you here. Here, second differences are all the same when the equation is quadratic. Okay, we like that. Now, we have that here. Okay, now what you need to know is that every time, and this is a good thing to write in your notes, when the second difference is 2, then the nth term will contain just n squared, like we had in this one. The second difference was 2. The equation for this was n tn equals n squared. So n squared. When the second difference isn't 2, but it's 4, that means the nth term, tn, right, will contain 2n squared. So in this case, our a up here would be 2. When the second difference, it's a bit like magic, isn't it? When the second difference is 6, the nth term, so tn, will contain 3 times n squared. And so on, and so forth. So when it's 8, tn will contain 4n squared, right? 3 times 2 is 6. 2 times 2 is 4. 1 times 2 is 2, etc. This is nice to remember so that you can just find these second differences and see, oh, okay, it's 4, so I already know that my A is going to be 2, right? Okay, so I can rewrite my formula now and say, because the second differences are 4, my A is going to be 2, Tn is 2 times n squared, okay, plus Bn plus C, because we don't know those yet, right? Now, because we only have 2 unknowns, we can go back to the way we solved that last problem here and just plug in 2 of the terms and then substitute one for the other. I know there's a pretty term for that. I can't get it right now.